Hey everybody, welcome back to our last video series on in this series we'll be discussing linear momentum, which will be the last topic that we cover for the year. Um, it's a very interesting topic, so we're going to get right into it. So I've attached the PDF packet of notes onto Schoology, so if you want to download it, you can fill it out with me, or you can follow along with the video here. So what is momentum? You've probably heard this word before in context of a lot of times it's used in the context of sports. One team will have the momentum, they say, and it sort of works in the same way in physics, but it's a little bit different. Um, what we're gonna really simply define it, but before we do that, I just want to relate it to the other things we've talked about this year. Just kind of do a full year recap. Um, so, and this will really give you an overall view of everything that we've studied this year. So, at the beginning of the year, we talked about mechanics, and we explained that objects will accelerate from rest to a final speed through some distance. We used the kinematic equations, um, and then we looked into the forces that cause those accelerations. And this is how we related these things. We used F equals ma, we used the kinematic equations, and we did all types of different things, including projectile motion, force diagrams. All of that falls under the window of mechanics, so to speak. And it's a way of explaining how and why things move the way that they move. And then we just looked at the last chapter. We looked at work and energy, and it's slightly different. We said, yeah, there's still forces, and these forces still cause acceleration, but they do so in a way because they're transferring energy. So we looked at it from the energy standpoint. Uh, a force acts on an object, it transfers some energy from one object into another object, and we call this phenomenon work. Forces are doing work, and that will cause an object's kinetic energy to change, which will in turn cause velocity change, cause acceleration. So we can still relate it back to our mechanics, but it's a little bit different. And then finally, what we're going to talk about today, and in this series, is this momentum idea. And the idea goes as this: an object experiences an acceleration due to some force acting on an object for an amount of time. So we could have said that before, right? We have an acceleration acting on, or we have a force acting on an object causing an acceleration. But what we're looking at is we're saying, okay, so if this force acts for a certain amount of time, um, this is causing an idea called impulse. So we have this idea here that the force provides an impulse on the object. We'll see this word come up a little bit later on. So now it's not forces doing work, it's not forces causing acceleration, but it's forces providing an impulse on an object. And this changes the momentum of the object. So now we're going to relate force to something we call impulse. So just to kind of, put everything together, we had, in this first chapter, we had F equals ma, and we had all these kinematic equations. So plus the kinematic equations. And that gave us our description of physics. And then in our second sort of context, we talked about work and energy, and we had this idea that work caused change in kinetic energy, and this work could also be described as a force acting on an object over a distance, the dot product of these vectors. And so again, we can see force, we can see kinetic energy. Energy is 1/2 mv squared, so we can see how these objects are related, how objects are moving. And then finally, when we're going to get into this chapter, we're going to relate force to something called impulse. And so what does that mean? What this equation, again, we're going to look at this in more detail later on in the series, but this is delta P, where p is momentum and t is time. So delta p over, and sometimes we even write delta t here instead of just t, indicating that it's some time interval. So this would be our change in momentum. And we'll define this a little bit later and talk about this more later on. But just to give you an idea that this is just another way of discussing how forces interact with objects. Okay, so we're gonna just get our formula down here. So just to kind of bring it back to what we were just discussing in kinetic energy, right? When we had kinetic energy, anything that was moving had kinetic energy. We had this idea that kinetic energy was 1/2 mv squared. And so anything that had a velocity would also have kinetic energy. So what we're going to say here is anything that is moving also has a momentum, right? So momentum is going to relate to velocity as well, but kinetic energy was a scalar quantity. This told us nothing about the direction that it was moving. So this was a scalar, not a vector. Now, when we discuss momentum, we're going to be now discussing momentum as a vector. All right, and so here's our formula finally that we're going to bring up here at the bottom of the page. And the idea here is that momentum equals mass times velocity. A very, very simple equation. You can see it actually is kind of similar to the kinetic energy in terms of it only depends on mass, only depends on velocity. Kinetic energy was a scalar, 1/2 mv squared. Momentum, there's no 1/2 term, it's just mass times velocity. Very, very simple, but notice there's a vector, right? So P stands for momentum. And if you're curious as to why they don't use another variable for momentum, well, one mass is already taken a little bit here by or M already is taken by mass. So, maybe we could do like big M or something like that for momentum. But initially, whenever Newton was publishing his papers, as the story goes, this is my history that I've learned anyway, is that the initial term he called for momentum was actually progress. So he termed it with the letter P. Later renamed to momentum. So whether that's true, I think it's true, but you could fact check me on that if you want. Um, okay, so what are the units for this? So we already know units for mass are kilograms and units for velocity are meters per second. And so momentum doesn't have any special units. We don't have newtons, we don't have joules like we had for kinetic energy. So units for momentum are simply kilograms times meters per second. So we're just going to combine the mass and the velocity. It does make it pretty easy to remember this because we just simply have our mass units and our velocity units. Oh, excuse me, I'm going to sneeze. All right, sorry about that. All right, so let's move on. So we have our equation. How do we apply this? All right, so on to page 3, we have this idea of collisions, momentum and collisions. This is what this is most interesting way to talk about momentum. Because when you talk about a moving object and it's just moving in a straight line, it's kind of boring. Uh, Nothing really changes. It just follows, our rules. If it's undergoing gravity, it's gonna, travel in a parabolic path. We've already talked about this enough. And if it's, if there's no forces acting on it, it's going to continue in a straight line as Newton's laws indicate. And so what we want to discuss here is what happens when objects collide. What happens when we have things like two or more objects coming together, either sticking together or bouncing off of each other. For instance, just the game of billiards or pool, as some of you might know it as. You hit the cue ball, it bounces into other balls and they go in all different directions. That's conservation of momentum right there that you're actually witnessing when you play that game. Whenever we have a big football collision between two players, right? And they run into each other, right? And you have both objects having momentum, and then at the end, after they collide, there's some momentum afterward. A lot of times their momentum will cancel out, or one player will have more momentum and will actually run through the other player. We could have this in terms of explosions. So if you have a single object with a lot of energy inside of it, and then there's some force exerted. So let's take, for example, like a grenade or something like that, right? And it breaks into all these different pieces of shrapnel. There's a single object and it's at rest. There's no momentum there. But after that explosion, all of the different objects are going to go in different directions, and um, we can actually map the pattern of all the shrapnel um, based on conservation of momentum. When we have one object colliding into many different objects, the momentum still has to be conserved. And then finally, this final concept that we really need is that we're gonna need two objects to interact with each other when we talk about momentum and collisions. So one object is kind of boring. I mean, we could talk about like a basketball bouncing off the ground. There's a collision there, but the ground's immovable, and it's not as interesting. But we'll see some of those examples of objects bouncing off of things. The most interesting examples are the ones that have collisions or explosions. Um, so when we have multiple objects interacting with each other, the point of all this is that this idea that momentum of a system is conserved. Well, what is a system? A system is our collection of objects. So this is why we will generally have more than one object. Anytime we have one or more objects, or two or more objects, we call that a system of objects. And we say that the momentum is conserved, which is going to just indicate by our equation that momentum initial equals momentum final. Right, and so let's look at just an example of this here. So, all right, so here we have example one, objects exploding apart. We have a rifle with a bullet loaded inside, and then the bullet fires and is traveling with some speed. So it says the bullet, whose mass is 50 grams, is fired horizontally with a speed of 1,100 meters per second by a rifle whose mass is 6 kilograms that is initially at rest. All right, so here we have the bullet. The bullet's located inside the chamber here. There's some gunpowder here that's going to explode inside the bullet and going to provide a force, and then the bullet is going to fire out of the gun. So everything here is at rest. The bullet's not moving, the gun's not moving. And if you've ever fired a gun before, you know that there's a thing called recoil, and you can feel it. The bullet fires. It has some speed, which is given here by muzzle velocity, 1,100 meters per second. And then the gun recoils with this velocity back the other way. And we want to know what the speed of the rifle recoil is here. And then just we're going to look at what is the initial momentum of the system and final momentum of the system and talk about that a little bit. Okay, so how do we figure out what this V rifle is? Let's rewrite the masses here. We know this is 50 grams, which is going to be 0.05 kilograms. And we know the mass of the rifle is 6 kilograms. All right, what we know is that momentum has to be conserved. So I actually want to answer these questions in a little bit of different order to help us understand. What is the initial momentum of the system? So well, first off, what is our system? Our system is our collection of objects. So in this case, our system is going to be the bullet and the rifle. And that's our system of objects, right? And then when we fire the gun, we still have our system. We still have our rifle moving one way and our bullet moving the other way. So if I look at the initial momentum of the system, right, P sub I, well, both masses are 6 and 0.05 respectively, but both velocities are 0. So any momentum, if I want to look at the momentum for the bullet initially, well, it's 0 because it doesn't have a velocity. And if I want to look at the momentum of the rifle initially, it's also 0 because it also doesn't have any velocity. So since the velocities are 0, my total initial momentum is 0. And you can see this is going to be similar to how we solved our energy problems. Right? Now, the final momentum of the system for, we could denote as P final, because momentum is conserved, this also has to equal 0. And this is because momentum is conserved. U there. All right, and so we can say initial momentum equals final momentum, just like we were able to say initial energy equals final energy. All right, and so where do we go from here? Very simply, since our initial momentum is 0, our final momentum is 0, what we know is our final momentum is going to be a combination of the momentum of the rifle and the momentum of the rifle final is going to be a vector that is pointing to the left and is indicated simply by the mass of the rifle times the velocity. And the velocity is also a vector that's going to the left. And so we're basically going to put a negative x hat in here to indicate that it's going to the left. Our velocity will end up being negative. This velocity, if we write it as a vector, is going to be positive x hat. And so we have our momentum for our bullet after it's fired is, again, mass 0.050 times its speed 1100 meters per second in the x hat direction, which gives us a momentum of let's see here, the bullet has positive momentum, 9.167 meters per second in the x hat direction. Oh, sorry, I forgot my units. I forgot my mass units. Oh, sorry. I'm messing up. Sorry, I copied the wrong number. This is our total momentum. Sorry, not velocity. Sorry. We'll see that number pop up in a second here. 0.05 times 1100 is 55. So we get the momentum of the bullet is 55 kilograms meters per second in the x hat direction, in the positive x hat direction. Now that means that my momentum of the rifle has to be equal and opposite to this, right? Since my final momentum is made up of these two added up, so I'm just going to go ahead and write that out. My final momentum is going to be the sum of the rifle's final momentum plus the bullet's final momentum. Right? And since we know that the rifle has a momentum of 6 times v rifle, and we know our final velocity is 0, our final momentum total is 0, we have 6 times v rifle And here we have 55 x hat kilograms meters per second. All right, and then this gets added over to the other side, and then we divide by 6, and finally we get that number that I wrote before, which was 9.167. You'll notice if we subtract this over and then divide, we're going to get a negative sign here, and the negative x hat, which is what we expected. So we get that V rifle is equal to final. V rifle final is equal to negative 9.167 meters per second. Now, this is 6 kilograms here. So just to show you where the units went, right? We had kilograms here. We had kilograms meters per second, which we're dividing. We subtract this over first, and we divide by kilograms. So the kilograms are going away, and we have left meters per second, which is our units for our final answer. And then there's also this x hat term, and the negative is indicating that it's going off in the opposite direction. So this would be our recoil speed of the gun as you fire it, and you would obviously be able to feel this, which is why you have to like brace it against your shoulder when you fire a rifle, and it has this little shoulder protector here. It's normally padded, so yeah, if you hold it away from your body and it recoils, then it's like you're throwing a 6 kilograms. 6 kilograms like 12, 13 pounds. So it's like you're throwing a 13 pound weight into your chest or into your shoulder at 10 meters per second. It's not going to feel very good. That's all just momentum conservation. All right, so we're going to do a few more examples in the next video, but I'm going to wrap that one up here. And so I'll talk to you guys tomorrow.